This talk is on plant interactions and limitations of growth within a forest community. And the forest, as we know, is never at a steady state. There's always constant change. Management from the top down often would look at pioneer species early and late succession and then kind of capping off the forest life with the climax forest. But we know there's much more to it than that. And management from the bottom up often entails looking at the microsite, the individual trees in the forest, and how they interact and grow together to help us better understand the total working of the forest. So how do trees interact? There's several theories out there. I don't know personally if I could take one side over another. Some may do that, and that's fine. But there are different theories out there. So I think it's worthwhile to be aware of different theories and look at them. One being mutualism. Historically, there was a time, I think maybe in the past, and even still today, there's some new research out there that showed that believed a forest lived in unison with all species and acted like a superorganism. So the forest was this giant organism, and if one segment of the forest, like one tree, fell down or was cut down, then it would affect the rest of the forest. A lot of people started looking away from that, I think, and into looking at the competition theory instead. And I don't even know if I can call that competition as a theory, but they look at that in some of the things that took place: introduction and elimination of species. There's always constant change within a forest, and new species are being introduced and old ones eliminated. Ash is one good example, and if we looked at in southern Ontario mutualism, then the death of all the ash would affect the rest of the forest. But typically the rest of the forest responds by, when there is ash dieback from EAB, that the other surviving trees react to that opportunity because there's more sunlight and things like that. So in that manner, behavior managed logs and logged forest stands, things like that, we look at that and say trees are competitive. They are going to outcompete other trees if they can for their own survival. And in that manner, competition is kind of how trees react. But at the same time, mutualism, if we go back to mutualism for a minute, with mycorrhizal associations, there are many times when that forest just might be a superorganism because of the mutualistic relationship that takes place between some species, because of other interactions within the forest, such as beneficial fungi, such as mycorrhiza. So within the establishment of a forest, when a forest has gone to the stand initiation stage, tree species are not random nor predestined. Okay, all trees have opportunity to grow on a site, whether it be one of the kind of the characteristic pioneer species like a poplar, or more of the later successional species such as beech or oak, or something like that. But the trees are influenced by the regeneration opportunities and the physical environment. Okay, so weather conditions as well as the other vegetation that plants might be competing with on the site are major factors. So we know that forests are difficult to predict sometimes because of the complexity within the forest, but when managing, we always do our best to try to find predictable and consistent patterns to help us kind of understand the forest stage and how it's developing, knowing full well that there is a chance that that we could be wrong, or major weather patterns or unforeseen circumstances might make changes. Species may also be classed together as a group associated with soil, climate, or after a stand disturbance. Okay, given the site, such as the soil conditions, the climate, and the weather patterns, and then the type of disturbance, the severity of the disturbance, and the availability of certain trees and seed to regenerate. Soil, climate, disturbances, and elevation, they're key factors that influence growth and limit growth, limit the opportunity for some species to grow. So the limitations are influential on the establishment of trees in forests. And what these limitations do is that it means that the site will not allow just any species to grow because they may not have the right environment that the seed needs to germinate in, for instance. Okay, so what this is doing is creating a niche environment where the site is, because of soil, climate, disturbances, and elevation, it's creating a unique growing space for a specific species to survive. And then on a larger scale, we can look at associated trees and associated forest types, and that can help give us some clues or help us to identify soil types, certain climate features, okay, habitat types for certain wildlife, the successional stage of the forest, how old it is, where it is along the age line of forests, if you will, and then also help provide indicator species. Indicator species of understory plants, of certain trees, and even wildlife can help us kind of determine the ecology of the forest or the stage of that forest. So where do trees grow best? What are your thoughts? Is it a xeric, mesic, or hydric site? First of all, do we know what these terms mean? Xeric, if you guessed dry, you would be correct. Hydric is more of a wet site, and mesic is not wet or dry, it's more of a well-drained type site. Okay. Where trees grow best, I guess to answer that first, is more of the mesic type soil. If a tree had a choice, in most cases you'd be talking kind of mesic, where if you had a soil that was like a moist, well-drained, sandy clay loam, that's making ideal growing conditions for a pretty diverse palette of species. But if every tree wanted to grow on a moist, well-drained, sandy clay loam, mesic site, that might be pretty limiting for other sites. And we know that not every site has this type of growing opportunity. So what about other soils? Why do trees grow there? To answer that, really, we have to look at why those trees are growing there and why others are not growing there. And so the answer to this is that trees typically grow where they compete successfully, not so much where they grow best. Okay, and why is that? The answer to that would be because there's too much competition where all the trees grow best. Okay, so using this chart, we've got our hydric, or quite wet sites, our more well-drained sites of mesic, and xeric being quite dry. Okay, so associated soils, you might be looking at more of a clay base here perhaps, and more of a sandy base up here. Okay, and you can see on this site, on the mesic site, that all of these species will grow in this area. So you could have black spruce, balsam fir, or jack pine all growing on a mesic site, but since they all grow there, there's a lot of competition. If you go up to the xeric site, you'll notice that black spruce and balsam fir, not so much because they can't tolerate that dry of a site. Okay, jack pine, it might not be their preferred site being up here. You can see that they would prefer being more back here. But up here, in this region, there's not as much competition, so there'll be more success for the species there. Okay, on the other side, the black spruce, same thing. On a spruce bog where it's really wet, you're going to have less competition from other species. It's not saying this is the best site for black spruce down here. Black spruce typically won't grow to its full potential, or will grow very slowly there because there's such an oxygen deprived site, but they can survive there where other species cannot. In climate gradients. So the vigor and competitiveness of trees varies with temperature and moisture conditions. So that climate, latitude, longitude is one, but also, especially in certain parts of Canada, we are also looking at elevation. Okay, so North Pole, South Pole, that's what I'm trying to talk about with the latitudes, equator, at sea level. That is obviously, there's a big climatic difference across that spectrum, but also up with elevation. In Canada, we've got lots of mountainous regions, and climate can change. Obviously, the snow-capped peaks here, right down to the forested areas down in the valleys. So there's lots of changes there. An elevation change of roughly 300 meters or 1,000 feet, so 1,000 feet or 300 meters up, is roughly equivalent to 160 kilometers of latitude. Okay, so and that's the change in hardiness zone. So species will change, one, as you go higher in elevation, but also as you go further north or south from the equator. Okay, and this in this 3D niche example, you're looking at climate and soil gradients in a three-dimensional scale. So here again we've got our wet, well-drained, dry sites. The elevation being the higher peaks here, and then down lower in the valleys down in at this end. Okay, and the competitiveness, you'll notice this is a west coast example, so we've got western species here, but you've got red alder. Okay, that is something that is extremely competitive, the most competitive of the other species mentioned, down low in more of the wet areas. So in the valleys and the wet areas of the mountains, you'll find the red alder. Douglas fir, as you get up onto drier sites, you'll find that being quite competitive all the way up into higher elevations. And then lodgepole pine is the least competitive of these three species, but is kind of the most widespread across the palette of sites. Okay, so climate and soil will affect which species are going to grow. They all have equal opportunity, and they can all probably grow on the site, but because some grow better in certain conditions, will make them or give them a more competitive advantage.